Hello, everyone. My name is Ben Armstrong. I am the executive director of the MIT Industrial Performance Center, and I'm excited to be able to share with you some of our research on automation and digital transformation in manufacturing. And to give you some context, a lot of our work focuses on the challenges of deploying automation at scale in manufacturing environments. For more beyond what I share today in this talk, you can look at our Harvard Business Review article from early this year. My colleague Julie Shah, who's a roboticist, and I, put together this framework for understanding how some firms automate more successfully than others. And it's a framework that I'll introduce you to today, but we go into more detail with more evidence in that article. Then we also have some work on the quality of jobs in terms of wages and upward mobility in manufacturing, and the role of those workforce changes in supporting a more automated manufacturing environment. So I want to start with some data. I'm going to focus on data from the US, but some of these trends are certainly present in EU countries as well. And the main chart, I think, that traces this history over time shows us that between about 1945, after the Second World War, and 1980, there's a positive equilibrium in manufacturing in the United States. You could see these lines, the yellowish line in manufacturing jobs, the red line capital expenditures, investment, new technology, the blue line value added, and the pink line wages. They're all going up. They're all growing together. So you see higher wage jobs, more technology on the factory floor, and more productivity. But with the rise of global competition in the early 1980s and disinvestment from U.S. manufacturing, deindustrialization of certain communities, you see a different trend begin to emerge. The capital expenditures, investment, new technology flattens. So too do manufacturing wages, and value added also flattens. So what ends up happening, employment goes down, productivity appears to go up, but it's only really going up because manufacturing work is decreasing. And ultimately, productivity flattens, and productivity in the United States has been declining, actually, for the last 10 years. So what can we attribute these trends to? If we disaggregate them a little bit, we find that at the factory level, the acquisition of new technologies has been quite low. So in US factories, only about 10% of firms have any robots at all. And then the trends are similar when we look at software applications. That acquisition of new software technologies are in less than half of all factories. And these technologies, as many of you know from your experience, are complementary. That it's hard to deploy robotic solutions at scale if you don't have software for monitoring, or software that can connect machines to, let's say, an ERP system to really get the most out of the productivity of your hardware. So ultimately, the lack of investment in technology is holding firms back in terms of getting the most out of capabilities of the tools they do have. And it's also affecting how they hire. So when we look at job postings in manufacturing, we find that fewer than 1 in 5 job postings for manufacturing workers, production workers in the US, require any digital skills at all. That could range from knowing how to use the Microsoft Office suite to developing machine learning algorithms. These manufacturing jobs are typically requiring only very basic non-digital skills. And this is important because we know that jobs requiring digital skills typically pay a higher wage, and they also can demonstrate more capabilities for productivity on the factory floor. If we look at cross-nationally, some of these are data on robot adoption, new robot installs per year. We find that we could look at Germany, we could also look at EU numbers, are similar to the German numbers here, that the new robot installations, this is really as representative of technology adoption more broadly, have been relatively flat over the last 10 years. A little bump in kind of the 2018 region, but even in the beginning of the pandemic at 2020, robot installations were going down. And given all the hype and excitement, particularly in university labs and among technology startups around robots and new technologies in manufacturing, I think it's a really interesting puzzle of why has adoption been relatively slow. And I'll speak a little bit about the red line that's growing dramatically here in China, which I think can be deceiving here. But a lot of our research focuses on the opportunity of adopting robots on the one hand, and slow adoption in practice on the other. And we say opportunity because studies from Finland, from the Netherlands, from France, from Canada, and from the United States all show that when firms do adopt these technologies, new robotic technologies, new automation software on the factory floor, they end up hiring more people, and they become more competitive than firms that don't. Now, you might think that firms that they're more competitive ex ante are more likely to adopt these technologies, and that's true, right? This is an association between adoption and performance, but it certainly is a positive one. And we don't find at the firm level that there's any relationship between adopting a robot and displacing workers, for example, which is an important counterpoint to a lot of the fear about robot adoption and work. So if we focus on kind of the counterpart to this question, we see low adoption of technology on the one hand, and we've also talked about flat wages and kind of challenging work, a low expectation of skills on the other. What I think is important to demonstrate is that manufacturing work during this period from 1960 to 2020 has changed quite a lot. In 1960, the average manufacturing worker in the United States without a college degree made significantly more, about 40% more than their non-manufacturing colleagues. So the gray line here represents the median manufacturing workers' wages, and then the green line represents the wages of someone with similar education who is in a non-manufacturing profession, sales or retail, for example. And what I think is striking from this figure is that over time, the wage premium, the gap between that gray line and the green line, is shrinking, until today, it's only about 2% difference. And in some regions of the United States, manufacturing workers actually make less on average than their alternative professions for those without a college degree. So what I think is important to emphasize here is that manufacturing jobs used to be really demonstrably good jobs, better than their alternatives for people without a four-year college degree. And today they're more comparable. So when we talk about labor shortages in manufacturing, difficulty to find workers, this is a big contributing factor. And I think that technology and digital transformation and automation can help address this, both by increasing the premium for manufacturing, improving the quality of manufacturing jobs, and also being a motivation for workers to come and work on the factory floor and have more opportunities for upward mobility. So just to bring these together, I want to give you a quick story from a factory that we work with in Ohio. So we've talked to a lot of factories through our work. We go and we visit and we ask questions like, can you take us through a new technology that you've acquired? Why did you acquire it? How did you use it? How did your workers adapt? What skills did they need? And through multiple visits with a firm in Ohio that produces parts for the aerospace industry, they're a defense contractor, and they produce a lot of high mix, low volume metal parts. The owner has lamented that he has the business to grow. He could double his revenue overnight if he had the workers to support that type of growth, but he can't really find the workers to do that. And this is, like many parts of the United States, he's facing a labor shortage in manufacturing, and he did before the pandemic. It's not just an artifact of the last 3 years. And what he knows is that in order to attract workers, he's going to need to offer higher wages. He's going to need to deal with this wage premium obstacle that I mentioned before. And the only way that he can offer those higher wages is if he improves this technology that he needs to automate. So he bought a universal robot, a collaborative robot arm, but he's had difficulty getting his workers to learn how to reprogram it and really welcome the robot as a tool on their factory floor. And this isn't just a problem for him in his relatively small shop with about 50 people. It's also a problem at large companies where we would expect automation to be welcomed with open arms and quite easy and be implemented quite swiftly. in Tesla's Model 3 factory, they've had a high profile issue. They had a high profile issue not being able to deliver cars on time because they invested too heavily, too quickly in robotic automation. Our colleague at Harvard, Yao Wenlei, has studied robot installations in China. In China, you might have noticed the red line in a previous figure showing Chinese robot installations going way up, mostly due to government subsidies. But Professor Lei's work shows that in some cases, in electronics assembly in particular, a lot of those robots were adopted, but were very difficult to use because they couldn't actually do the delicate work required in electronics assembly contexts. And then finally, from some of our colleagues' work in MIT's Work of the Future task force, they found that the idea of a lights out factory with perfect robotic automation wasn't even the goal for various manufacturing owners, partly because there was some kind of trade-off between pursuing total automation and continuing to innovate and improve on a process. So really, what we've learned from these observations at large factories through our own work at small and medium factories is that automation's hard, and it's hard for a few different reasons. One is that the technologies themselves aren't easily adaptable. They're built to be really robust and reliable to do repetitive tasks, but hard to reprogram between tasks. And oftentimes when you do try to reprogram, they need various skills, technical skills that the process experts on the factory floor might not have. And then finally is that when you get into more advanced systems and you try to add flexibility, the systems become a black box, and it's tough to know why a system is, why a robotic system that's, for example, using vision or AI is doing the task that it's supposed to do. And in most manufacturing contexts, you want to be able to explain why you're getting the outcome that you're getting. And with a lot of new algorithmic techniques, you can't actually get that explanation readily, which is a barrier to using it on the factory floor. So what the goal of our research has been, and I'll kind of move into kind of our framework moving forward, is to figure out how we can develop and deploy automation technologies in manufacturing that are improving productivity, so that have the robustness and reliability of typical automation that can improve the throughput per labor hour, but also have enough flexibility to make them adaptable to different environments. And we've noticed this because in a lot of cases, particularly small and medium firms, that if they bring in a robotic integrator to help them establish a robot use case, they would need that integrator to come in and work on the next use case and the next one and the next one. So they end up relying on this third party rather than using the robot as a tool internally, like they would their CNC machines to produce the various parts that they're shipping to customers. So the question really is how automation technologies can be flexible in the same way as a CNC platform might be for existing manufacturers. And here's the framework, really the path to flexible automation that we've developed. And we call it positive sum automation in the sense that we want automation that's both good for the productivity of the firm and also good for the flexibility and job quality of the worker. So really a win-win. And we think that there are three elements to this. One is on the design of the technology. And this is where my colleague Julie Shah works on low code and no code programming interfaces for automation technologies, where it's easier for shop floor workers to use and adapt these technologies to different applications. And the goal is to reduce the switching costs for these tools between different part numbers or even totally different uses on the factory floor. And then that design element, the low code, no code, easily accessible design, really bleeds into the integration question. Rather than relying on third-party integrators and outside skills, the idea is that the process expertise that factories already have can now become integration expertise, where process experts can easily integrate tools to the purposes where they need them. And instead of having this black box system, it's a system that you can understand and use and adapt for your own purposes. And then finally, we think that there's a real need to redefine how we measure success in terms of automation. A lot of the ROI calculations that we see off the shelf and we see even technology providers using emphasize the performance of a technology versus the performance of a human. And this is this competition of can the robot do better at the task than a human is a zero-sum game. And I think, in reframing this as a positive sum investment, we want to understand if the robot and the human can do better together than a team without that's not enabled with technology. So really, we're looking for overall performance improvements from the robot human team and not a competition between